Dear colleagues, let us continue our session, and the next talk will be given by Ihor Havrylenko. He's from Karazin Kharkiv National University, and the title of the talk is Stability of Minimal Surfaces in Three-Dimensional Sub-Riemannian Lie groups. Please.
Дякую за слово. Спочатку хотів подякувати організаторам конференції за те, що в такий складний час збираєте і дозволяєте проводити, значить, такі онлайн-конференції. Ну, тема англійською заявлена, тому я спробую розповідати англійською, так? So, my topic stability of minimal surfaces in three-dimensional sub-Riemannian Lie groups. A sub-Riemannian manifold is a smooth manifold M together with a completely non-integrable smooth distribution H on M. It is called a horizontal distribution and a smooth field of Euclidean scalar product on H. It is called a sub-Riemannian metric. In particular, can be constructed as the restriction of some Riemannian metric on M to H. Here we will assume that all sub-Riemannian structure are of this form. Let be sigma a smooth oriental surface in a three-dimensional sub-Riemannian manifold M. If an H is the orthogonal projection of the unit normal field N of sigma in the Riemannian sense, onto H and the sigma is the Riemannian area form of sigma, then the sub-Riemannian area of domain is defined as the normal variation of the surface sigma defined by a smooth function U is the map where I is an open neighborhood of 0 in R and XP is the Riemannian exponential map at P. In other words, we construct the variation in the traditional Riemannian way by drawing the geodesic to each point P and sigma in the direction of the normal vector U from P and from P. Denote R from S, where sigma S equals phi S from sigma. Then the first derivative R at 0 is called the first normal area variation defined by phi, and the second derivative R at 0 is called the second one. A surface sigma is called minimal if the first at 0 equals 0 for any normal variation with compact support in sigma without sigma 0, where sigma 0 equals P and sigma such that an H from P equals 0. Is the singular set of sigma. Note that here we will also follow the Riemannian traditions by defining minimal surfaces at stationary points of the sub-Riemannian area functional. A minimal surface sigma is called stable if second derivative are at 0 greater or equals 0 for any normal variations with compact support in sigma without sigma 0. Sorry. Так. We will call a surface sigma in a three-dimensional sub-Riemannian manifold vertical if TP sigma is perpendicular to HP for each P in sigma. Here the normal vectors of these planes are orthogonal. In particular for such surfaces and h equals n and sigma 0 equals empty set. In we proved that a vertical surface sigma is minimal in the sub-Riemannian sense if and only if it is minimal in the Riemannian sense, and derived the following second variation formula. Where nabla and Rik are the Riemannian connection and the Ricci tensor of M respectively. X is the unit normal vector field of H, which is tangent to sigma because it is vertical. Nabla sigma and B are the Riemannian gradient and the second fundamental form of sigma respectively. Follows that is sigma is stable in the sub-Riemannian sense, then it is also stable in the Riemannian sense. The three-dimensional Riemannian Heisenberg group, also known as the three-dimensional Thurston geometry, is the space R3 with coordinates x, y, z, and which the following orthonormal frame of left invariant vector fields defined by its null-potently group structure. Theorem. Let a sub-Riemannian structure of nil be defined by a left invariant two-dimensional horizontal distribution, then its normal field should be of the form: if lambda equals mu equals 0, then a complete connected vertical surface in this sub-Riemannian manifold is minimal if and only if it is a vertical Euclidean plane. If the other case, it is minimal if and only if it is a vertical Euclidean plane over a straight line on the xy plane that has the direction lambda mu. All these surfaces are stable in the sub-Riemannian sense and thus in the Riemannian sense. The three-dimensional Thurston geometry solve in the space R3 with coordinates x, y, z and with the following orthonormal frame of left invariant vector fields defined by its solve Lie groups structure. Let a sub-Riemannian structure on Sol be defined by a left invariant two-dimensional horizontal distribution. Then its normal field should be of the form where lambda mu not equals 0. Theorem: if nu not equals 0, then a complete connected vertical surfaces in this sub-Riemannian manifold is minimal if and only if it is cylindrical and can be parametrized either as or as. If nu equals 0, then a complete connected vertical surfaces is minimal if and only if it is a horizontal Euclidean plane z equals z0 or lambda equals plus minus mu, and the surfaces is hyperbolic helicoid with the parametrization. All these surfaces are stable in the sub-Riemannian sense and that in the Riemannian sense. The three-dimensional Thurston geometry SL2R can be described as the universal covering of the unit tangent bundle of the hyperbolic plane H2 with the Sasaki metric that is the half space with the following orthonormal frame of vector fields. Note that the fields y1 and y2 here are not left invariant with respect to the Lie group structure of SL2R. A two-dimensional horizontal distribution choose a normal field X is a linear combination of the fields y1, y2, y3 with constant coefficients defines a sub-Riemannian structure SL2R. E is its horizontal distribution if and only if X is of the form where lambda not equals -1. This sub-Riemannian structure allows vertical minimal surfaces only for lambda equals 0 and lambda equals 1. Theorem: if mu not equals 0, then a complete connected vertical surface is minimal if and only if it is a half plane x equals x0 for lambda equals 0 or a half plane z equals z0 for lambda equals 1. If mu equals 0 and lambda equals 1, when a complete connected vertical surface is a minimal if and only if it is either a half plane z equals z0 or cylinder that can be parameterized as if mu equals lambda equals 0, when a complete connected vertical surface is minimal if and only if is cylinder over a geodesic in H2. All these surfaces are stable in the sub-Riemannian sense and thus in the Riemannian sense. On the other hand, the fields form an orthonormal frame of left invariant vector fields with respect to the simple Lie group structure of SL2R and the sum metric. Note then x1 Lie brackets x2 x3 thus a left invariant horizontal distribution defines a sub-Riemannian structure on SL2R. For its vertical minimal surfaces, we have the following. In fact, a similar description up to an isometry will take place for any sub-Riemannian structure of the form theorem. A complete connected vertical surfaces is minimal if and only if it is either a half plane z equals p half plus pk or a helicoidal surfaces with one of the following parameterizations. Pure minimal half planes and helicoidal surfaces from the first two classes are stable in the sub-Riemannian sense and thus in the Riemannian sense. Thank you.
Thank you very much, Igor. Thank you.